Watertracks are extremely common in the foothills region of the Brooks Range. Of course, because they're on hill slopes, you need a hill slope for there to be a watertrack. You don't have watertracks out on the coastal plain area.
Watertracks, which are kind of different than anything you'd see outside of the Arctic region. They're unchannelized, so unlike a stream which has, clear banks and a bed, these are areas on hill slopes that are more or less linear regions where most of the water flows below the surface.
They don't form a channel that transports very much sediment or cobbles, but they do drain the hill slope of water.
My name is Caitlin Rushlow. I'm a PhD student right now at Idaho State University, and I'm working with Dr. Sarah Godsey and Dr. Tamara on the Watertracks project. We're looking at the coupled hydrology and biogeochemistry of watertracks, and I'm specifically working on the physical hydrology side of the project. Yeah, okay.
One of the challenges of our work is trying to understand how much water there is, how nutrients are transformed in those water tracks. And really one of the reasons that we care about this is that we don't have these features elsewhere. They're really related to permafrost, so they rely on there being frozen soil.
Anywhere that there's permafrost, that influences where and how water moves through catchments. Water doesn't move through frozen soils and it flows over the permafrost. Places that lack permafrost or have discontinuous permafrost have areas where water can leach more deeply into the soils and then move more slowly through and out of catchments. Where permafrost is present, and especially in the Arctic, the depths of soils that water can move through are very shallow. And so water's interacting mostly with organic soil.
All we're doing today is measuring discharge, water discharge. To do that, we use an instrument that measures water conductivity. And so we'll put it in the water downstream and measure what the background conductivity is. And then we'll dump a salt slug in upstream. So the water itself will mix it by the time it gets to the probe down our reach.
So we're measuring the flow of water using dilution of salt. So I know exactly how much salt is just table salt that I added, and then that conductivity value is representative of the amount of salt in the stream. And so we're just watching for dilution of that salt, and the amount of dilution is due to how much water is in the stream.
It will, go up and down, and then we integrate under the curve, and that gives us our discharge. So that's it. It's really simple. It's a good method for small streams where instead of using water velocity meter, because it's so shallow, you can just dump a little bit of salt, and it doesn't hurt anything because it's such a small amount and it just flushes right out.
We have a full year of data and samples analyzed this current field season that we're in, all of those bottles of water in the freezer, and Caitlin is working through calculations from her loggers. And so about this winter, we'll start to have some good answers. We have some observational answers. We know how quickly they respond to precipitation, for example. We know that the hydraulic head suggests that water is moving from the hill slope to the water track. We know that huge fluxes of solutes happen during snowmelt, and then elements become very scarce later on during the year. And so they're transporting a lot of material during snowmelt, and then those elements become very low concentrations this time of year.
We have many hypotheses about watertracks, and there's not a lot that's known about them. So there are many questions we can answer, I think, and that's really the point here, is to understand more about the Arctic, specifically water and nutrient use in the Arctic. Streams are fairly well understood, but the link between the terrestrial and the aquatic environment is less well understood.